you. Sorry. Okay, hello everyone. Am I audible to all of you? Okay, great. So we'll continue exactly from where we left yesterday. And again, for first half at least, we will not be working on R, and then we'll start.
Hi, Deepak.
Yes,
Yes.
Emma,
Sorry for interrupting, but can you please pass me the host rights?
I'll do that. I'll do that.
Thank you, Deepak.
Okay, can I continue?
Deepak, I have received the host rights and you can continue with the session.
Okay, so we're going to start exactly from where we left yesterday and quick recap. What did we do yesterday? We started with inferential statistics, right? And all of you know what is now null hypothesis and alternate hypothesis? Yes? Okay, great. So let me open Excel and so all of you know how to construct. Okay, so between null and alternate hypothesis, which of the hypothesis will you construct first? We discussed that yesterday many times. No, I told you that alternate. It's easy because it is the claim that uh, is to be tested and it is easy to distinguish, right? So between null and alternate, always construct alternate first. Okay. Okay. Let me just start with an example and then we'll continue, right? Just reviewing null and alternate, right? I'll just start with a couple of examples and then we will continue from errors, right? The type of errors that you can make. In, okay. Example one. A mm, school teacher claimed that his uh, schools, his, okay, let me put it, okay. A maths teacher claims that his students are score more than average. Okay, that is students score more than average than the rest of the students in other classes. Okay, historically, the average maths score in the school was 75%. Construct the null and alternate hypothesis. Yes, quickly. As you construct null and alternate, I'll also write another question. Both, construct both null and alternate. Let others also respond, those who want to respond. I'll just wait for 30 more seconds and then we'll start. The average running time. Okay. So everyone, I think I've got consistent results. Alternate is, so let me put H0 is null, HA or H, let me put HA, alternate. So H0, sorry, first I'm going to construct alternate, which is clearly given in the question. Mass average score were greater than 75%. So alternate is uh, score greater than 75% is what is claimed, right? And rest, everything I'm going to put in null. Score less than equal to, right? Everyone has the same, everyone has constructed same null and alternate. Anyone who has a confusion can let me know still. Otherwise, I'm going to go to the next example and then we'll. Okay, great. So average mm, running time 50 seconds. Okay. Quickly. Okay. H0 is going to be Ungori. See what is claiming, what is to be proved. The newly trained runners claimed to run less than 50 seconds. So what is claimed? That is to be proved. And that will become alternate. Okay. Is that clear, Pungori? So null H0 will be, sorry, seconds or time in seconds greater than equal to 50, and HA will be, just turn this around. Okay, so practice. See, you can get lot of examples, right? Using this, I mean, on the web. If you want to practice this, do practice. There will be lot of examples on the web, or even when you go through the content, maybe video recordings and all, right? So practice it. Always remember, I'm telling you, I mentioned yesterday also. One sentence will, I mean, just erase all your confusion if you just remember one sentence. What is to be claimed will be put in alternate, and just adding to that, do not put equal. Equality will only come in null. That's it. If you remember these two sentences, you will never ever get confused on this. Okay? Just remember these two sentences. Okay? Okay, great. So let's continue, right? So yesterday we had done null alternate. Now tell me, we what do we try to do in inferential? We try to infer about the population based on small samples, right? Yes? Everyone with me? So, do you think when we follow such a process of making inferences about the population, do you think we can make errors? Do you think errors are possible? Tell me. Do you think errors are possible? Yes, of course they are possible, isn't it? There can be a lot of errors. I mean, there can be a, I mean, a good chance of errors, because we are just taking a handful of samples, and we are trying to predict the huge population, isn't it? Right? So, errors in inferential. Now, what do you think can be the type of errors? Just think. What do you think can be the type of errors? Okay. Let me make your task easy, right? Sampling error, right? Okay. See, sampling error happens, of course, when your samples are not uh, representing the population, right? That they can happen, right? But I'm saying in taking the decision, what errors can happen, right? Okay. Let me make your task easier, right? Null. What options do you have? Null and alternate, right? We try to predict, right? Predict or infer. On the other hand, what can be the actual situation also? Null and alternate only. Actually, also these two situations can happen. Either we are going, actually, the there is no change, which is null, or there is change, that is alternate. And we also try to infer the same thing, right? These are actual and these are null, right? So what do you think? Where do you think we can make errors? Rather, I'll just reverse this, alternate and null, right? Where do you think I'm making error? If actually it is null, I am also inferring null. Will I make error? Will I make a error here? Actual situation is also null, and I also infer null. Did I make error? Pungori, you're not listening to me. No, we did not make error here, right? Similarly, if the actual situation is that there is a change and my samples also indicated that there is a change, did I make an error here? Did I make an error here? Again, don't listen, Pradeep. I am saying actually also there is a change and my samples also indicated a change. So did I make an error here? No. Again, no. Right? So where are the errors made? Now listen to me very carefully. Actually, the situation did not change, but my samples indicated a change. Did I make an error? Yes. Similarly, actually, there was a change, but my samples indicated no change. Another error. Are you getting it? How can you make errors? Are you getting this? And I think who mentioned it? Alok. Yeah, Alok mentioned it. Accepting wrong hypothesis, rejecting correct hypothesis. Yes, correct. Right? So, accepting a wrong hypothesis and rejecting a correct hypothesis means correct alternate. Right? Rejecting a correct alternate and accepting a wrong null. Right? Okay, right. So in nutshell, I have just explained you. Now let's discuss these errors in detail, right? And I'm going to introduce you to some terminology that is statistics terminology. It's not. I've just mentioned this as type one and the other one as type two randomly. Okay. So now when I say H0 is true, just think H0 is true actually, right? This is actual situation. H0 is true actually means H0 is true means actually there was no change. Let's talk in terms of the example that we were discussing yesterday, open air gym, right? Actually the null was true means the male weight did not reduce. It remained 80, right? Okay. But my samples indicated that I should reject the null. Means my sample, the sample that I collected, it was not indicating that the male weight remains same. It indicated that the male weight reduce. So in that case, I'll reject null. Yes, I will reject null in that case. Correct, right? So rejecting a true null means actually null condition existed after even after government efforts, actually no change happened, but my sample indicated a change and we based on the sample I rejected the null. I made a type 1 error and this is called alpha. Type 1 error and alpha are statistical terms. You will not, I mean, these are standard statistical terms. So type 1 error or alpha is rejecting a true null hypothesis. Yes, RT-PCR. Can you tell? Yeah, RT-PCR test. Okay. So test indicated a COVID positive case, but actually the case was the person did not have COVID, right? But the test indicated positive. So rejecting a true null. We rejected a null, true null, and we went on and the test result was given that COVID was there. Correct. Not having corona, but the test is saying positive. Yeah, that's what I said, right? Is that clear? false positive. It is also called false positive. If you are getting confused with this, false positive, just think it as positive means change. Yeah, Idris, don't go that fast. Confusion matrix. Yeah, I know you know it very well. We will come to confusion matrix, right? Yeah, this is also a type of confusion matrix, but let's not bring in more terms. Let's go step by step. Okay. Okay. Right. So false positive. This is also called false positive. Why? We are wrongly going with the positive change. Actually, there was no change. Is that clear? This type 1 error is clear to all of you? Type 1 error is also called alpha. It is you if you want to by heart it, but this from a we can say interview perspective, if you are giving interview or from any if you are just appearing for any test or you want to test yourself, this is a very very important slide. Okay, so very important. If you want to by heart it. Type 1 error is rejecting a true null hypothesis. Okay, and of course going with the change. Clear? Now type 2 error. Let's see what are the type 2 errors. What is the type 2 error? Fail to reject a false null. We fail to reject a false null, right? So we'll call these as false negatives. Type 2 error. Okay, and this is called beta. This is called beta. It is also sometimes called no, sorry, 1 minus beta is called power of test. Sorry. Yeah, this is also called beta. So having corona, yeah, as Amatullah said, you have corona, but your test indicated that you do not have corona. Is that clear? You have corona, but the test wrongly indicates that you are all fit and fine. Is this clear? Type 1 and type 2 errors are clear to all of you. Let me know if there is any confusion, else we will proceed. Quick. If you want a minute to absorb, you can tell me so that I know at least you are absorbing it. Otherwise, we'll proceed. So I think I should proceed. Nobody is responding. Am I audible also? I sometimes start testing the mic, checking the mic, because when I don't get response from a batch which is of decent size, then I have to check my mic, na, if there is no response. Okay, so this is clear to all of you, right? Okay, on the flip side, the blue quadrants, true positives means actually H0 was false, means actually change occurred and we also rejected H0. So no error, right? True positives. Okay, true negatives. There was no change and my sample also indicated no change. Okay, true negatives. Clear? Okay, now quickly I want you to, okay, we'll first discuss these. Okay, difference between type 1 and type 2 error. Type 1 error, non-acceptance of a true null. Is this clear to all of you? Non-acceptance of a true null means rejecting a true null hypothesis, right? That is what we are doing. Okay? Yes? Type 2 error. Acceptance of a false null. Wrongly, I am accepting a false null. Actually, New condition. Actually, an alternate is true, but I am wrongly accepting a false null. Clear? Difference is clear? False positive, false negative. Now, represents a false hit means you are wrongly hitting the you're wrongly hitting. Okay? A miss. This is a miss. Okay? You miss the positive and you go with the wrong negative. Okay? Probability of error is called alpha here. It's called beta here. Right? This is called level of significance. Alpha is called level of significance. We are going to work with level of significance a lot, so understand this very well. Alpha is also called level of significance. Okay? Example, new drug is accepted, but it is not effective. Right? The same thing that we discussed about corona. Right? New drug is accepted, but it is not effective. Right? It got accepted, but it was not effective. Rejecting a newly effective drug is a type 2 error. Right? We rejected a newly effective drug and we said it is not effective. Okay, that's a type 2 error. Is that clear? Difference between type 1 and type 2? Okay. Now I want you to go through this on your own. It's an example of a bank customer, right? Bank customer, all of you would have gone to bank sometime, opened an account, taken a loan, taken a personal loan, car loan, sometimes, right? Whenever you go to a bank, banks ask you to fill a form, fill some form, right? For loan, they will ask you to fill so many forms that I mean, you will get fed up also, right? They'll ask you to sign so many times that after that you will never forget your signature. You can do your signature even, you will be doing your signature even in your dreams that day, right? Okay. So now, do you think when they ask you some information, they are just randomly asking you some information? No, they are scientifically asking the information that they want you to tell. And it's not that the information they ask you, they are just piling up some forms and just keeping it in. No, it's the information they ask you is scientifically tested and then it is put in the models to predict whether you are a good customer for them or a bad customer for them. Okay? And this is done by all the financial institutions these days. Okay? So you went to a bank, right? What kind of errors bank can make, right? Suppose you are a good customer, right? But bank, build your details, and they put it in the model, and their model told that reject the null. You are reject the good customer, and they said you are you are not a good customer. Maybe good customer means maybe they are expecting that you might do a default, so they don't give loan to you. Okay, you are a good customer, you don't have such intentions, and H0 is true. Let's assume you are a good customer, very similar to that of the court case, right? No, uh, assume the defendant or the person who is convicted is not guilty, right? Yes, same way, right? Assume you are a good customer, and actually you were a good customer, but the bank rejected you. So they rejected a true null hypothesis. They made a type 1 error, rejecting a good customer. Is that clear? Now, what is the other error they can make? You had some malicious intentions. Maybe you wanted to um, default, right? Now, if you feel bad, don't take your friend as a default person who is going to default. Okay, this is just an example. Okay, okay. If you get offended, then don't take it on you. Okay, so good. You had some malicious intentions. You wanted to default, but and bank accepted. Bank gave you the loan. So from your perspective, it was good, right? But from bank's perspective, they made a wrong decision, right? They said you are a good customer, but actually you defaulted the next month. Okay? Yeah, Vijay Mallya, yes, right? Anyways, that was a planned story, but yeah, I mean, you can take that case, right? So, what did that was another error they made. Now, we accepted a bad customer and thus we incurred bad debt. So, bank accepted a wrong customer and incurred bad debts, right? Failed to reject a false null. Bank said, okay, the customer is good, but he was not good. The second type of error. Is this clear? In terms of bank, the two types of errors. Is this clear to all of you? Right? Okay. And the blue quadrants, no error was made. Their model indicated that he is a bad customer and he was also a bad customer. So bank was able to avoid bad debts. This is called power of the test, 1 minus beta. Okay. It is also called power of test. Okay. And true negative, identifying the true negatives. Bank do not reject a good customer, means they identify the good customer as good and hence give the loan. So no error was made. Okay. Errors are clear to all of you. Another example, but you can do it on your own later, right? Another very interesting example, weather forecast example. You can do it on your own later. Okay. Now coming to the further steps of hypothesis. Three steps we have done here, or rather 2.5 steps we have done, and then we are going to do the remaining three, and then after that we will go to R. Once we understand the entire process, remaining process of taking decision, then we go to R and we will construct the different types of hypothesis. We'll do the different types of hypothesis testing. Okay. Before I proceed, one thing that I think I should have mentioned yesterday. Let's take a look at these 1, 2, and 3 examples. Right? We did these yesterday. Right? So company has held a 23% market share of product A. There was an increased marketing effort, hence the company believed that its market share is now greater than 23. Right? So can you tell me on which side of the on which side of 23 I am going to test my claim? If this was 23, right? On which side I am going to test my claim? Everyone? Right side? Everyone with me? Everyone with, yeah, all of you are saying right. Very good, right? So I believe it's the concept is has sink in well, right? Okay. Here, on which side I'm going to test my claim? On which side of 40 I'm going to test my claim? Left side? Everyone says left. Very good, right? Now, the third example. On which side I'm going to test my claim? Both the sides? Excellent, right? So remember this, whenever you have a equality symbol in H0, only equality symbol, you are going to test the claim on both the sides. In this case, in these cases where you have greater than equal to or less than equal to, you test the claim on one side. Is that clear? Easy? I mean, nothing complicated, just that I missed this yesterday, right? So I thought I'll just take it up. Okay? Okay. Now moving to the steps in hypothesis testing. So setting the null hypothesis, we have done. Setting the alternate hypothesis, we have done. Setting the significance level, we will discuss. Then after you do this, select the distribution test. There are different distributions which we are going to learn, right? And then among these distributions which I have to select, we will learn these in fourth step. Then calculating the p-value. What is this p-value and how this p-value helps you take the decision? We are going to learn this. And the sixth, take decision, that is accept or fail to, sorry, reject or fail to reject the null. Okay, reject null or fail to reject the null. Okay, so this is just a summary, high level summary. Now coming to the details of the steps, right? First two we have already done, setting a null, setting alternate, and we know how to do it. Okay, so I am just running on these slides, running over these, right? Third step, setting the significance level, which is alpha, and the critical region, right? So let's understand this. What is alpha? We just discussed. Type 1 error, right? Significance level or alpha is the maximum probability of accepting a type 1 error, right? That is, we reject a true null hypothesis. That is, when we reject a true null hypothesis and assume that a significant change has occurred. Is that clear? So significance level is the maximum probability of accepting a type 1 error. Is this clear? It's called alpha. We have already discussed this. In hypothesis, there are actually three types of three levels of significance level, or sorry, three you can say levels of alpha, right? We'll discuss that. Now let's see this picture, right? Suppose this is a distribution of the sampling distribution of sample means. Remember that it takes the shape of normal curve, right? So we can easily draw a sampling distribution of sample means even without knowing what was the uh, shape of the population, actual population, right? Okay, and if you remember, in a normal curve, the entire area represents 100%, right? Mean is in the middle and 50% on each side, right? 50% area on each side, right? So in hypothesis, as I said, there are three common significance levels: 1%, 5%, and 10%. Okay, if you want to be very stringent on errors, you are going to be selecting alpha as 1. If you want to be very relaxed with errors, you will say, okay, you can accept 10% errors. You are going to accept 10% errors with the samples that you are taking. Okay. Otherwise, if nothing is given, which is 95% of the cases, right, we just take, and if nothing is given around significance level, right, we safely assume it to be 5%. Is that clear? Is this clear to all of you? Okay. Now tell me, alpha is the probability of type 1 error, which is the, or rather, alpha is the maximum probability of making a type 1 error, or maximum probability of accepting a type 1 error, right? So if I say that my sample that I'm picking, right, there is a 5% probability of error in that case, right? Phi alpha is 5%. There is a 5% chance that this sample may give me a wrong prediction or wrong inferences about the population, right? So how much percentage confidence you will have on your sample? Very good and very quick also. Everyone agrees with Pungori? Yes? 95% confidence, right? So always remember this: 1 minus alpha is called confidence level. Okay? It is the probability with which we accept the null when true. Okay? The selection of significance level depends on the business. Yeah, this is like the second point, as I've already discussed. If you want to test very stringent levels of errors, you are not taking very few errors. You want to test your sample at a very preciseness. With preciseness, you will go with 1%. If you are okay and maybe you don't want it to be very stringent, you will go with 10%. Okay. So this is clear. What is confidence level also? Okay. Now, for one tail test, the level of significance, that is alpha, lies on either side of the distribution, left or right, isn't it? If you are going to test the claim on either side, whether left or right? So, on where will you make the error? Only on that side which you are testing, isn't it? Yes. The test where on which side you are testing the claim, the error will also be made on that side, na? Right? So these are called one tail test. On the other hand, if you are testing your claim on both the sides, you can make error on both the sides, isn't it? Yes. So that is called a two tail test. The total level of significance will be split. Now in two tail test, your alpha will get split on both the sides. Very, very logical, isn't it? I don't have any one side. I'm not preferring any one side, right? Or I'm not weighing, putting a weight on any one side, right? I'm going to simply split my alpha on both the sides. Means on either side, the maximum probability of error that I'm going to accept is alpha by 2. Is that clear? Such a test is called a two-tail test. Any confusions on this? One-tail and two-tail test? So we can proceed, right? Okay. Now tell me, this red line is my alpha, right? What is alpha? Tell me what is alpha? Significance level. What is significance level? The maximum probability of accepting a type 1 error, right? Remember this. Means you are ready to take sample, you are ready to accept a sample, what you are ready to accept what the sample is indicating when you know that, yeah, you know that I am ready to accept 5% error, right? You are ready to accept a sample up to 5% errors, right? Now tell me, you pulled up a sample and when you tested it, it indicated that the it indicated that the actual error rate of that sample is 3%. Okay, will you accept that sample or will you reject that sample? Re- we will okay, I'll reframe it. I'm saying you are ready to accept 5% error rate, right? When you pulled a sample, it indicated that the new model from which, or the new population from which it has been pulled, it is only 3% error rate. Will you go with this new 3% error rate? Yes, because it has less uh, risk, right? It has less error, right? You'll go with 3%, means you are going to go with the new situation. You are going to reject the null, isn't it? Are you getting my point? You will reject the null and you will go with the 3% error population, right? Everyone with me, right? So what does this mean? If this was 5%, if this was alpha is equal to 5%, right? Where will 3% lie? On this side, isn't it? 3% is going to lie on this side only, na? Yes, right? So this region, wherein this region, wherein which will lead you to reject the null, right? And go with the new situation, go with the change situation, is called critical region. Are you getting this point? Critical region is a set of all values of test statistic. I'll explain what is test statistic. For now, just understand 3%, right? 3% that would cause a rejection of the null, right? It is the observed test statistics in the critical region that then if the observed test statistics is in the critical region, then we reject the null hypothesis and accept the alternate hypothesis. Are you getting it? So if your if your sample indicated that actually the rate, actual error rate is going to be only 3%, but you were ready to accept 5%. So you will happily go with that sample, that actual, right? Actual case, right? Okay. On the flip side, if you pick a sample and it indicated that the error rate is going to be, the actual error rate is going to be 10% or let's say 20%, will you go with that change? Will you go with that change? No, you will not go with that change, right? Let's say it was 15% or 20%, 15%, right? Will you go with that change? No, we will stick with the null because here if the new situation is far more riskier than my 5% that I am ready to accept. Are you getting this point? So I in such a case the where the actual error rate is going to be greater than alpha, right? I will not go with I will not go with alternate, and I'm going to I'm going to fail to reject the null. Sorry, I'm going to, yeah, fail to reject the null, right? So this side, you reject the null, and this side, you fail to reject the null. Is this clear? Any confusion on this? Okay. Now, so this is called critical region because it leads to a rejection of the null. That is why it's called a critical region. Now we will talk about this 3 and 15%. How did I arrive at that? We'll talk about that shortly. Okay. I just gave you an example that this is called a critical region because here any value that falls on this extreme side would cause a rejection of the null. Okay. Okay, so critical region in a one-tail test will be on one side. In a two-tail test, critical region will be on both the sides. Okay, because I can reject the null on either side when I'm testing on both the sides. Okay. Next, now coming to how did we arrive at that 3% and 15% that I was talking about, right? There should be a mechanism to arrive at those, right? How did we arrive at those numbers? Because I know that my rate of accepting error is 5%, which I have fixed. But how did I get the 3% and 15% with which I will compare 5, right? For those, we get that number from distribution tests, right? These distribution, there are different types of distribution test. We are going to do z-test, t-test, ANOVA and chi-square, right? These three, z, t and ANOVA, are known as parametric test, and they are based on the assumption that the distribution is going to be normal. Okay, that, and so they are called parametric test, z-test, t-test and ANOVA. Okay, and chi-square assumes, does not make any assumption about the normality of the the data set or the population. Okay, and th- that is called a non-parametric test. We will see the difference between parametric and non-parametric shortly, right? So what happens is we are going to first select these types, which type these tests, right? Which of the tests we are going to do. There are some conditions. I'm going to discuss that shortly, right? Based on that, we get based z test. If I select z test, it will yield a z score. If I select t test, it will yield a t score. If I select ANOVA, it will yield F statistic. And if I select chi-square, it's going to give me a chi-square statistic, right? So these are called test statistic, right? Then these test statistics, along with the significance level that we are testing, which is 5%, right, are used to calculate the critical values. Okay, and critical value is the value that divides the rejection region with the non-rejection region, right? We'll see this process. First, let's understand when do we use z-test, t-test, ANOVA. Okay, so for that, mm, okay, so let's understand when do we use these tests. Okay, z-test, t-test, ANOVA. Okay, so when you have an information that the population is normally distributed, okay, your data is normally distributed, first condition is you will use either of the three. You will not use chi-square. Chi-square is used when you have a information, when you have no information about the normality or no assumption about the normality of the data. Is that okay? Normality of the distribution. Okay. So if you have information that the data is normally distributed, you will use either Z, T or ANOVA. Now Z test and T test are used when you compare two sets of data, either sample with population or two samples, right? Or okay, in both these cases, we compare two sets of data. And then we use Z test when population standard deviation is known and n is greater than 30. Is that clear? Is that clear? Okay. We use t-test when, of course, population is normally distributed and I'm comparing two sets of data and the population standard deviation is unknown or n is greater than less than 30. N means the sample size. Okay. So if you have information that n is the sample size is 15, so what test you will use? T test. Everyone with everyone on the same page, right? If you have information that the population is normally distributed and the standard deviation is known, which test you will use? Z test, right? Now, when you have to compare more than two sets of data, right? I want to compare, let's say, I want, I have uh, IQ scores of school 1, school 2, and school 3, right? I have the IQ scores I've taken samples of the IQ scores from three schools, right, or three institutions, whatever you want to call, right? I want to test whether all the three belong to a same population. When I say this, all the three belong to a same population, take it as that they have the same population parameters. They have the same characteristics. Their population has the same characteristics. Okay. So whether I want to test whether all the three belong to the same population, I'm going to use ANOVA because more than two samples. Is this clear? Okay. And in case I do not have any information about the normality of the data, I will use chi-square. Is this clear? Four four tests. Is this clear to all of you? No response. Okay, fine. So now coming back to our PPT, right? So once you decide which test is to be used, right? Z test will yield a Z score, T test will yield a T score, F test, F statistic, ANOVA, F statistic, and chi-square generates chi-square statistic, right? Using these test statistic with along with the significance level, we basically look at some tables which you do not, whatever I am explaining this process, it is just now, you can say, just conceptual part, that this happens at the back end, right? 10 years back when these softwares were not there, 10-15 years back, we used to do these, or maybe some of you would have done these in your high school also, manually, right? I'm going to show you one example. How do we take decision manually, right? So from these tests, we get something called critical value. Okay, using these test statistic along with the significance level, we get critical value. Okay, and then that critical value we compare with p value, right? So P, what is this P value now? Let's understand this P value. Okay. P value, again, it's a standard term, is the observed test statistic, right? Is the observed means actual, that actual risk, or actual, that 3% and 15%. Remember, this is the actual test statistic. Okay. It's the calculated probability of the actual event. Actual event that that has occurred. It is the calculated probability of that event, right? So p value we compare with the critical value, right? And then we take a decision. P value is also called the cumulative probability of outcomes as extreme or more extreme than the observed value arising by chance. So it is the cumulative value of all the events, all the extreme events, right? If this is a p value, all these events which occur on these side, if I cumulate them, that will give me a value of that will give me p value, right? Extreme basically, right? All the events that has these extreme occurrence probability will give me a p value. That is why it said cumulative probability of all outcomes as extreme or more extreme than the observed. Okay, it is the area under the tail. Now p value is called the area under the tail of the probability distribution, and it is also called the evidence against the null hypothesis. Why it is called evidence against the null, we'll see. Because smaller the p value, stronger is the evidence that you should reject the null. How is this? Suppose p value, suppose my significance level is alpha, alpha is 5%, and I have two p values, 1% and 3%, right? So, right, so 1% has more stronger evidence that I should reject the null, right? Because it is far more extreme than 5 than 3%, right? That is what it said. Smaller the p value, stronger is the evidence that you should reject the null. Is that clear? Right? So let's understand p value along with significance level and see how do we take the decision. Now, p value is the actual risk we carry in the model. That is why it is said, I mentioned here, it is the calculated probability of the actual event, means it is the calculated probability of the risk, 3%. Remember, I told you it is the actual. Suppose the sample indicated that the actual risk is, actual error rate is 3%, right? So it is the actual risk or the error rate that we carry in the model when the event occurs. That is called p value. Okay. Here risk means the probability of type 1 error, that is alpha. That is when we reject a true null hypothesis, right? We can also call p value as an actual significance level. You can also call it as actual significance level. See, one is alpha, which is the desired significance level, right? Because I am ready to accept 5% error, but when the actual event occurred, I found out that the risk is only 3%. So I will be happy to take that. I will be happy to go with that event, right? That new event, which is only having 5% or 3% error, right? So that is called p value. Now, if we can, we can also call p value as the actual significance level. Also, significance level or alpha is the desired probability of type 1 error. We have already done this. That is the acceptable level of risk, right? Now, when p value is less than alpha, it means actual risk in the model is less than the desired risk, right? Thus, we reject the status quo. I've already discussed this, right? And we conclude that the change is statistically significant and we reject null and we go with the alternate. This is clear? And alternatively, the second case is when p value is greater than alpha, 15% risk. It means actual risk of moving to H0, of moving of the new model, the actual risk of moving to H0 of the new model is greater than the desired risk, right? Rather, it should be H1, right? Actual risk of moving to H1 means alternate of the new model is greater than the desired risk. Thus, we reject the status quo H0 and we conclude that the change is not statistically significant. Hence, we fail to reject the null. Is that clear? So this should be A of moving to HA. Are you getting this? Those who are doing it for the first time, it might sound tricky, right? But don't be scared. When you are going to hear this, the recordings 1 or 2 times, it will make sense and it will get fixed in your mind. Okay? And for people, those who already know this, I'm sure you would have got the essence of our discussion. Right? Any confusion still here? Let me know. Else we will go on the last step, take the decision. So this is actually the same thing, but I have just explained it. P value is less than when p-value is less than significance level, we reject the null. You can see this in the visualization, right? Now, lower p-value means lower the likelihood of the uh, risk, right? Lower p-value means lower the likelihood of the risk. It means that it is less likely that such a sample can be picked up from the population, right? Means I am more confident that such a sample came from a different population, hence we reject the null. Okay, Idris says if p-value is equal to significance level, what do we do? Then it's a business case to decide. Then it's up to business to decide. Okay, then business have to take a decision whether they are ready to accept that. Okay, and the otherwise, higher p-value means higher the likelihood of the risk, right? It means it is more likely that such a sample can be picked up from an existing population, right? More likely that such a sample can be picked up from the existing population means I am more confident that such a sample came from this population only, hence we fail to reject the null. Okay, so this is the entire process. I have just summarized it in this. You can, I mean, this single slide summarizes everything, right? These are the critical values, alpha by 2, right? This is 1 minus alpha, rejection region on both the sides, and non-rejection region in between, right? Now what we'll do is, so that we get an idea of how the manual, whatever we have discussed, how do we, how are these manual steps done, right? I will uh, just discuss one example, right? And after this we will go to R, right? This is the example. I will discuss this manual steps, right? Okay, so a, a principal at a certain school claims that his students has above average intelligence. Okay, a random sample of 30 students IQ score have a mean of 109. Remember this, right? A random sample. The sample indicated a mean of 109 of sample of 30 students. Notice this. So 30 students, and you also know the standard deviation. Notice, is there a sufficient evidence to support the principal claim? The mean population is 100. Notice, the mean population IQ score is 100 with a standard deviation of 15. So can you tell me which test we are going to use here? Everyone, z-test. Why do you say z-test? Let's get the answer on that also. Why do you say first sample is 30? Very good. Second, standard deviation is also known. Population standard deviation is also known, right? So it means we will use z-test. Everyone with me? Okay. Okay, great. Next. So let's construct a null and alternate. Let me see who can construct null and alternate without looking at the screen. Yes. Construct null and alternate. I don't know if this window was able to hide null and alternate, but I want you to construct null and alternate on your own. Okay. Alternate is greater than 100. Very good. Amatullah, why less than 100? What you want to test? 109. 109 is greater than 100, right? Idris, why 109? Mean is 100 only, na? Yes, Idris also corrected it. Very good. So, right? So, see, if you're doing it for the first time, it's okay to make such mistakes so that you also remember it next time, right? One mistake, one or two mistakes are always welcome, right? But of course, making a mistake again and again is not advisable, right? Yeah, that's okay. That's okay. I understand, right? Okay, perfect, right? So null and alternate is clear. Now we want to test the claim of the principal, which says that the mean score is 109, or you can say it's greater than 100, right? So this is our alternate and this is our null, right? So nothing is given. So what significance level I will assume? 5%, right? So I have taken alpha as 5%. Okay. So now what happens is rejection region or area of 0.5 is equal to now I know I'm going to use Z table, right? I also know the value of alpha, right? So remember I told you from the Z table, from when you know the test, right? You along with significance level, you go to the tables, right? Okay, from this we first calculate from the Z. Now when I know that it's a Z test, I calculate the Z score, right, or the Z statistic, right? How do you calculate Z statistic? It is calculated by this formula, which is uh, this. Can you see this in line number 19, which is X bar means X bar is sample mean, right? Sample mean minus population mean, right? Divided by, this is a formula I will discuss, right? When we do Z test, right? In R, we will discuss this concept, right? Divided by under root of N, right? Under root, how do I write? SQRT N. Okay, this is a formula. This gives you the Z statistic. Okay, or also called Z score, right? Now we calculate the Z score for this, and then we we look at this Z score at 5% significance level table, right? So this Z score I have calculated, which comes out to be, see, this is the calculation of Z score. Okay, 109 minus 100 upon square root of 30. Okay, and this comes out to be what is this? 15. Oh, I think I've written the formula wrongly. It's under root. Yeah, the formula is wait. I'll show you the formula. I've written it wrongly here, right? The formula is did I mention it here? I think it will be better if I show you on the slide. I'll just show you. Statistics. Sorry. This is the formula. Okay, but we don't have to remember this. This gives you the Z statistic. Okay, sample mean minus population mean upon standard deviation, and standard deviation divided by under root of n, right? So we have the standard deviation also 15, right? And this is what is calculated here, which gives me the Z score. Okay, now I look at this Z score in Z tables and I get the, this is 3.28, right? So I'll look at this table 3.28, somewhere here. This is 8. That 995. This is the number, and this Z table, these tables used to, this table would give me the uh, area under the, on the left side of the curve, okay, of this. So area on the left side is 995. It means the area on the right side, and this will give you the p value, is 1 minus triple nine 0.995, right? This will give you the p value. So you will compare this p value to, this is how you arrive at, first of all, this is how you arrive at the p value, okay? But again, as I said, you don't have to do all this. When we will do in R, all you have to do is simply, it will give you p value, and you just have to compare it with the significance level, okay? This, all this dirty work is not required to be done, okay? So when you get the p value, you just compare it with alpha. So p value is 0.0005, which is far less than alpha. Hence we reject the null, because p is less than alpha. So we reject the null, and we say that the principal claim is correct, that the mean score, because the mean score of the 30 students is 109, so the principal claim is correct, that and we will go with the alternate hypothesis, okay? So this is how the things used to be done 15 years back, when you did not have any software. But now we'll see how this entire process is done in just a single line of code in R, okay? And we'll see that once we start with parametric and non-parametric tests. And the first type of test we'll do is Z test, okay, right? So before we start with parametric and non-parametric tests, first we will understand what are parametric and non-parametric tests, and then we will understand what is degrees of freedom, right? And then after you do degrees of freedom, we'll start with Z test. Okay, so let's start with parametric and non-parametric tests. Okay, so as I said, parametric, I've already discussed in brief. Parametric tests are the tests that are based on the assumption of normality, right? So if you look here in the Excel, they assumes normal distribution, that population is normally distributed, okay? And non-parametric test does not make such assumptions, okay? And there are, I've already discussed, Z test, T test, ANOVA are parametric test, and chi-square is a non-parametric test. There are other non-parametric tests like Wilcoxon rank, Mann-Whitney, which are not in our curriculum. We are going to only do chi-square. Okay. So let's discuss what are parametric tests. Parametric test makes an assumption about the distribution of the data. They assume normally distributed data, right? Non-parametric test does not make any assumption about the distribution of the data. Hence, they are also sometimes called distribution-free tests. Is this clear? First point. They are called distribution-free tests because they do not make any assumptions on the normality of the data. Okay. Parametric tests used in the data that is normally distributed, used in the data that are other than normal distributions. Same point, right? Parametric test deals with mean and variance. Very important, right? Population parameters. Remember the word? Population parameters. They deal with population parameters, population mean and population standard deviation. Okay, hence they are called parametric test. Non-parametric test deals with other summary, you can say other summary statistics like medians, right? Some ranked data when the sample size is very small, or when there are presence of outliers. In under such circumstances, we use non-parametric test. Is that clear? Okay. Now I think I missed this point, deals with median and variance. It is parametric test is used to estimate at least one population parameter, right? Mean or standard deviation from the sample statistics, sample mean and sample standard deviation. This point is clear? Okay, next. Parametric test data is on continuous scale measurement, interval or ratio. Clear? For parametric test, we have the data which is on the continuous scale. For non-parametric test, data is categorical in nature, right? Like rank. Okay. So we do not have when we do not have any information or we know that our data is not continuous, we will go with non-parametric test. Okay. We know that our data is ordinal, ranked, we'll go with non-parametric. Okay. Parametric test, information about population parameter is completely known by means of population parameters. Okay, sorry, I'll repeat. Information about the population is completely known by the means of population parameter. Thus, the statistic test is called parametric test. Hence, this test is called parametric test because we are testing population parameters. We are inferring the population parameters. Okay. In non-parametric test, no knowledge about the population parameter or no knowledge about the population or its parameters, and it is still required to be tested, then we use non-parametric tests. Parametric are inferential statistics. Even this is inferential. Even non-parametric is also inferential. Okay, but we do not have information about the population parameters. Okay, no knowledge about the population or its parameters. Okay, H0 is made on the parameters of the population. We have seen either it is mean, right, or sometimes it is standard deviation also, right? But in non-parametric, H0 is free from population parameter. We do not make an assumption about the population parameters in non-parametric. Okay. Okay. Now this point is very important. Please understand it very well. This point. Though I'm sure you would have got an understanding about the difference, but this point is actually the crux of the main difference. Parametric tests are powerful as the parameters and the statistics are calculated on the original data. Means it uses all the data points to calculate the parameters. When you calculate mean or when you calculate standard deviation, we are using all the data points. Yes? Yes or no? Yes? Hence, they are powerful tests because they are using the entire data, information from entire data. Now, when you talk about non-parametric tests, they are not that powerful because there is a loss of information when we calculate ranks, right? Suppose you only have information about ranks of some numbers, right? Let me show it to you. It will be better. Suppose I have five numbers, right? 54, 200, 324, 100, and let's say 80, right? This is my actual data. This is my actual data, right? Now, I have been given only the ranks for this, right? Ranks in terms of 1, 2, 3, 4, and 5. I only have this ranks. I don't have this. Let's say I hide it. Now, based on this, do you think if I have the rank, do you think I actually have information about the data, entire information about the data? No, right? It is only giving me the order, right? So that is why it says when you're dealing with rank or when you're dealing with median, I can still calculate the median. This number is my median, right? When I have the rank, I can calculate this as the median. This number was the median, but actually I don't have the numbers, right? Right? Are you getting it? So either when you're dealing with median or you're dealing with rank, I am I don't have information, complete information. There is a loss of information, right? Thus, the impact of the magnitude of the data is lost. I don't, magnitude means this difference, the magnitude of this data, the differences between these numbers and the mean, the, that information is not there. The impact of that magnitude is lost in non-parametric tests. Hence, they are not that powerful than parametric tests. Is this point clear? Right? So yes, you are right, Amatullah. Non-parametric tests can be done on qualitative data. We will see that, right? Qualitative means like gender, count of gender. You can still do non-parametric tests, but they will not be as strong or as powerful than parametric tests. Okay, clear? So this is these are the main differences of parametric, non-parametric tests. Okay, data types we have already done. Degrees of freedom, right? Let's do this. Okay, we'll do this after the break, right? Yeah. I forgot the break also. Sorry about that. Quickly, before you leave, please do participate in the poll. Let us know how did we do in terms of pace and delivery. Very important for us. So, and then we take a 17 minutes break. Don't worry on that, right? So please just spend 5 seconds on this poll and then leave, uh, go for a break, and uh, I'll put a timer, right? Thank you so much. Appreciate your patience. And I put a timer. I'll be putting the timer on the screen, and really appreciate your participation in the poll because that really helps us in understanding that whether we were meeting your expectations or not, right? And when we come back, we will continue. Exactly, do come back as per the timer. Thank you so much. Hello everyone, welcome back. Thank you so much for participating in the poll. So we'll continue. First, give me a confirmation if I'm audible. Am I audible? Okay, thanks Alok for the response. Okay, so before the break, we discussed and understood parametric and non-parametric tests, right? Now, there is a concept of degrees of freedom that is used while we when we do these tests. So let's understand what do you mean by degrees of freedom. Okay, so degrees of freedom in statistics indicate the number of independent values that can vary in an analysis without breaking any constraint, right? They are the number of values that are free to vary in the data set. Now, what does this mean? Right? Let's discuss it. Let me discuss degrees of freedom with the help of an example. Okay, it is an estimate of the number of independent pieces of information that went into calculating the estimate. It's not quite same as the number of items in the sample. So let's understand this degrees of freedom. Uh, okay, let's say this is my data. Okay, and I know that the sum of my 5 data points, right, is 100. Okay, the sum is 100. So hence the mean is going to be divided by 5, right? So mean will be 100 by 5, right? Now, what does degrees of freedom mean? 1, 2, 3, 4, and 5. So my data has 5 observations, right? So am I? Can I put any value in one? Can I put any value in one? Any value? Right? I can put any value in one, na? Why? Why, Pungodi? Why can't I put any value? If the sum of 5 numbers is 100, am I not free to put any value in one? Yes, right? I can put 20, I can put 25, I can even put minus 200. Right? That's an extreme value, but I can put any value, even minus 1000 also. Right? But let's not go that extreme. Let's say I put 25, or let's put, okay, 28. Right? In second, am I free to put any value in second also? Yes. 32. Just randomly I'm putting. Third also I'm free to put 1. Fourth also I'm free to put 6. Uh, 42. Right? Now tell me, am I free to put the fifth value? No. Right? I am not free. The way I put the first 4 values freely, I cannot put the fifth value freely because I have a constraint that the sum of these 5 numbers is 100. So the fifth value has to be 100 minus the sum of these numbers, whatever it be. It came out to be minus 3, right? So if I just want it to be uh, positive, I'll put it as 34, right? So the fifth value came out to be 5. Is that clear? Now when so so degrees of freedom means the values I am free to put. How many values I was free to put? How many values were I was able to put freely? 4 or n minus 1. Yes, right? Or n minus 1, right? So that is called degrees of freedom. The 4 values that I could put freely, that is called degrees of freedom. Is that clear? Indicates the number of independent values that can vary in an analysis without breaking the constant. Okay, so I've given an example here which I've already discussed. It's the same example, I mean a similar example, that if I have if I've been given that the sum is 100 or the mean is 20 for 5 values. First 4 values I'm free to put. I can pick any number for the first 4 values. But of course, once I pick the 4 values, the fifth I cannot freely choose, right? Okay, great. Uh, uh, thanks for your encouraging words. Okay, great. Right. So degrees of freedom is clear. Okay. Now let's start the tests. Right. Let's start with Z test. So all of you remember the conditions when we will use Z test. Yes. First condition is assumption of normality. Second is the population standard deviation is also known. And third is either of them, right? Either population standard deviation is known or n is greater than 30, right? And of course, yeah, two groups. Yes, that's very important, right? That is in fact implied because, I mean, when you have three groups, you'll go for ANOVA. The only decision you have to make is whether you have to use T test or Z test, right? Okay, great. So let's start with Z test. Okay. Before we do Z test, right, let's understand the concept of standard normal distribution, right? All of us know normal distribution, right? What is normal distribution? You know, right? Bell curve, exactly. Now, see, let's take a look at this picture, right? There can be normal distributions can be of various types, right? All of these are normal distributions if you see them closely. Let's look at red one, right? Red one is a normal distribution. It's a bell-shaped curve, right? Symmetric around the mean. Let's take a look at orange one, then green one, and then this purple one. All these are normal distributions, right? And then you have this thicker one, blue one, right? Now, what is standard normal distribution? It's a normal distribution only, which is standardized in terms of mean and standard deviation, right? Means means this blue distribution has a mean of 0 and a standard deviation of 1. Okay, so standard deviation equal to 1 and mean equal to 0. This is the properties, or this is the, you can say, the, yeah, properties of standard normal distribution, that it will have mean equal to 0 and standard deviation equal to 1. Okay, yeah, of course, mean is equal to mean, median is equal to mode. is always there for all the normal distributions. Okay, but now why do we? What we do is we convert all different any type of normal distribution into a standard normal distribution. Okay, and why do we do that? Standard normal distribution is called a Z distribution. It is a unique normal distribution where mean is equal to 0 and standard deviation is equal to 1, and area under the standard normal distribution is 1 unit. So area under this curve is considered as 1 unit. Okay, normal distribution can be standardized by converting it into z-scores. Z-score tells you how many standard deviation from the mean each value lies, right? So when we convert normal distribution into standard normal distribution, we convert the x, which is there on x-axis, that is our unit, right, into z-score. Okay, in a standard normal distribution, you'll see on the x-axis you find z-score. Yeah, it is Amatullah. I'll come to that again, right? It is for every normal curve, mean is equal to median is equal to mode. That is a property of normal curve. Okay, normal distribution rather. Okay, now standard normal distribution is nothing but a probability distribution. The area under the curve between 2 points tells you the probability of variable taking the range of value. I'll explain this, but why do we convert it into a standard normal distribution? Let's understand this. What is the benefit? What are the benefits of standard normal distribution? The data points are referred to as x in the normal distribution, and they are called z-scores, right? So what happens is when you have a normal distribution, on x-axis you had x variable, right? That gets converted into z-score, right? And the formula for z-score is this: x minus mu, means x means the observation, mu means the population mean, right, divided by population standard deviation. Okay, this will give me a z-score for each value. It will, this is how you standardize the normal distribution. Okay, a z-score is a standard score that tells you how many standard deviation away from the mean an individual x lies. Means if, let me show you, yeah, see, z-score is nothing but the standard deviation in a standard normal distribution, right? So if my x, if my mean is 0 and in a standard normal distribution it says plus minus 1 standard deviation, so it means it is saying that a z of -1 that and +1, right? So in a normal distribution, mu plus minus 1 standard deviation would hold values 68.2%. 68.2% of the values lie between plus minus 1 standard deviation, right? Remember that? And that turns to be plus minus 1z in standard normal distribution. Okay, so why are we converting it into a standard normal distribution? Because if I ask you to compare this red distribution with orange, right, it becomes really difficult to compare them. Yes, it becomes very difficult to compare these two. So what we do is we convert both of these into a standard normal distribution, which is this blue curve, right? How do I convert this red into a blue. See, red has a mean of 0 but a standard deviation of 0.5. 0.5 because, can you tell me why it has a standard deviation of 0.5? Because the deviation, if you will see the extreme values in red, they are much lesser than the extreme values of blue. Yes? And blue is a standard normal distribution which has a standard deviation of 1, right? So, of course, any distribution which has a width less than blue will have a standard deviation less than 1. Okay? Are you getting this point? Yes? No? Idris? Okay. Idris, tell me. Yeah, I'll explain once more, no problem. Explain. Idris, tell me, this is clear that blue is a standard normal distribution and it has a standard deviation of 1. This is clear? Right? Yeah, blue is clear. Now tell me, just observe blue and red and tell me where do you think there is more variability? Blue, right? And blue has a standard deviation of 1. So, can you tell me what will be the standard deviation of red? It will be at least less than 1 because the variability is less. So that's what I was saying. Now, that's what I said, that any distribution which is having a width lesser than blue would have a standard deviation less than 1. Okay? Got it? Okay, so how do I convert this red into a blue? I squeeze it from the top, right? If I squeeze this, just consider that these are like balloons. If I squeeze it from the top, what will happen? All this data which is here, right? It will be reduced because I squeeze it and it will get filled up in these. Yes? Yes, are you clear? Yes? So, all this data will be filled up here and this red will be converted into a standard normal distribution. This is called normalization. This procedure is called normalization of the distribution. Okay. Similarly, for purple, what will I do? I'm going to squeeze from both the sides, right? And I'm going to squeeze it so that this peak will increase to blue and this additional data here is going to be filled or compensated on this top, right? Is this clear? Again, notice that in the case of pink, mean is 0 because this is the center point for all the distributions except these three distributions. This is the central point and all of them have a mean of 0, right? But what is the standard deviation of pink? Oh, sorry, purple. What is the standard deviation of purple? 2. Isn't it more than blue? Right? So when you have a distribution which has a standard deviation more than blue, I will have to squeeze it from both the sides and normalize it so that it takes the shape of the standard normal distribution. Okay? And similarly, now in the case of orange and red, see, now mean is standard deviation remains same. See, orange, blue and red. Notice that orange, blue and red, their shapes are same. Only the placement is different. Orange, blue and green, sorry, not red, my bad. Yeah. Orange, blue and green, yes. The shapes are exactly the same, only that the placement is different. Are you getting this point? This is green, this is blue, and this is orange. So how do you normalize in that case? We shift orange from here to here. Basically, we shift the mean. Here the mean is -1. Here the mean is 1. We shift the mean to 0 by shifting here. Is this clear? How do you standardize these? And these standardization can be done using this formula. This formula helps you standardize and convert your X and standard deviation into Z scores, right? So Z score is something that is there on the X axis of standard normal distribution. Okay. So this is clear, standard normal distribution. Why do we need standard normal distribution? To compare Z scores on different distribution with different means and standard deviation, normalize scores for statistical decision making, find the probability of observation in a distribution falling above or below the given value, right? And find the probability that a sample mean significantly differs from a population mean. Under all these circumstances or all these situations, we would need to convert the distribution into standard normal distribution. Okay. Now coming to Z-test. Statistical test to determine if two population means are different when the variance are known and the sample size is large. Large sample size is sample size greater than 30 is considered to be a large sample size. Okay. So when the sample size is large and the variance is known, means population standard deviation is known, we will use Z-test. Used to test hypothesis in which the Z-test follow the normal distribution, very true. Also, T-test assumes standard deviation. T-test assume the standard deviation unknown, while Z-test assume it to be known. So the difference between T and Z is when you do not know the population standard deviation, we will go with T-test. Okay. I've discussed this. Okay. When do we use Z-test? Simple. Samples are drawn at random. Samples are taken from independent population. Population variance is known and sample size is greater than or equal to 30. Under these circumstances, we will use Z-test. Some assumptions of Z-test. Scale of measurement is continuous or ordinal, right? Data is collected from a representative randomly selected data. Distribution is normal and there is homogeneity of variance. So these are the assumptions of Z-test. Okay, now the formula to calculate Z statistic, I've already showed this to you, right? So let's do this. Now we have done Z-test. Theoretically we have done the concept part of Z-test. Now let's go into R and do this Z-test. Okay, so we'll go into R. All of you please open R Studio. Homogeneity of variance means homogeneity. Amatullah, homogeneity of variance means when two samples are there, right? It will assume that the variance is homogeneous, means in the same range, similar variance. Okay, when two samples are there. Okay, but you don't worry about these assumptions. They are just theoretical unless until you really need to test them. Not required to be remembered when you're doing data analytics. Okay. Okay. So everyone on R. Okay, before you start, I want you to download this package called R Commander. R is capital and CMDR, R Commander. Download and install this package. Don't activate it. We'll use it in some time. Not for Z test. Okay? We'll use this in some time. Okay. Uh, Once you're done, it might take 2 minutes. So I'll just wait. Once you're done with R Commander, just type R in the chat window. Okay, it might take 2 minutes. I'll just wait. Error in installing package object R Commander not found. Can you share the code? Amatullah? Quotes. Can you see? Package name of the package is in quotes. Okay. So you can just install it. A script will run and then we'll later on work on it, right? But let's discuss some examples for Z distribution, right? So we are not going to do a Z test, right? Rather, we will do T test, right? But we will discuss some examples wherein Z distribution is used. Okay? Let's see this example. The test scores of an entrance exam fit a normal distribution with a mean test score of 72 and standard deviation of 15.2. So can you tell me what is this 72 and 15.2? What is 72 and 15.2? Mean and standard deviation, I know it's mean and standard deviation, it's written also. No, it's population mean and population standard deviation, isn't it? It says the test score fit a normal distribution, right? Nobody did. Am I mentioning the sample data here? It is just saying the population, these are population parameters. I wanted to hear this. These are population parameters, isn't it? Everyone agrees with me? See, that is what you have to figure out. Very, when you read any question or when you read the details, just figure out exactly what is it. Okay? Okay. So test scores of an entrance exam fit the normal distribution with the mean test score of 72 and standard deviation of 15.2. Compute the percentage of students scoring 84 or more. Now see what is it asked for. Let me create a distribution, normal distribution. This is a normal distribution. Tell me, what should I put here? Who will tell me? What should I put here? What is this line? Yes, what is mu? 0? 72. Idris, why 15.2? This is the position of a mean. 15.2 is not mean, it is standard deviation. $72. Okay? Yeah, that's okay. If you have replied it by mistake, I'm happy. But if you have replied it after thinking and conceptually, then I'm worried. Thinking, right? So if you have replied by mistake, fine. Okay? So this is 72. Okay? It says find the percentage of students scoring 84 or more. Okay? So what you have to find? This cutoff, this is 84, means this is 84. And what you have to find? Find the percentage of students. So basically you have to find this shaded region. Yes? Clear? Now coming to our commands in R, right? P-norm used to get the probability, that is area under the curve. D-norm gives the density at a single point. And you don't have to do Q norm and R norm, just exclude those. So P norm gives you the probability or the area under the curve, right? And P norm, the syntax of P norm is this. P norm, first you mention the mean. First you mention the X, then you mention the mean, then you mention the standard deviation, and then whether it's a lower tail, this uh, this shaded area is on the lower side or upper side, right? So if it is on the upper side, you'll mention lower tail equal to false. If it is on the lower side, you mention lower tail is equal to true. Is that clear? And what will you get when you will run this? You will get the probability of 84, this shaded region. Okay? So let's run a P norm. Explain the lower tail, please. Yeah, Idris, lower tail equal to false means where exactly your shaded region is. If the shaded region is on the lower side, right, you will mention you are asking P norm to give the probability on the lower side. Okay, but if you want the probability on the higher side, upper side, we want probability on the upper side, now 84 or more. Okay, so if you want the probability on the upper side of this, you will mention lower tail equal to false. It automatically means give me the probability on the upper side. Is that clear? Yeah, right side. Yes, yes, yes. You are right. It's on the right side, I mean. Okay, upper side means right side. Okay, so let's see this. P norm, first you mention the x value, then you mention the mean, then standard deviation, and then mention lower tail equal to false. Quickly run this and tell me what answer do you get. What answer did you get when you run P norm 2149? It means 21.49% of the students scored 84 or more. Clear? Now let's see this. If I change it to true, run it and see. Isn't it on the lower side of that? Isn't it the lower value? Idris, especially for you. 0.78. Isn't it 1 minus 21.49? So it means now, okay, let me modify this question a bit, right? So this was 72. Right now we have already calculated 84, right? Now I want you to tell me what is the percentage of students who got scores less than 50? Let me see who will tell me. Who will tell me this first? P norm, P norm 50, mean equal to 72, standard deviation equal to 15.2, and lower tail, what should I do? Lower tail equal to true, right? Answer comes to be 7.38. Is that clear to all of you? Okay. Now one more variation of this. So part A, how many what is the percentage of students who scored less than 50, right? B, what percentage of students scored between 50 and 75, 75? Okay, let me see who can do it. So less than 50 was 0.74. Okay, very good. Amatullah has calculated. What about others? Anyone else who has calculated? This should be the answer. 0.50. Let's see those who are calculating it. Okay, let's see what logic should you follow. Let's see what logic should you follow. This is my normal distribution. This is 72. I am saying what is the percentage of students who fall between 50? 50 is on one side and 75 is on other side, right? So I want the area between this, right, and this, correct? Yes, everyone with me? Now I've already calculated the area on the lower side of the 50, lower side of 50. What was it? It was 0738, right? So on the upper side of 50 means I'll calculate this entire area, which comes to be 0.92, right? From that area, I subtract the area on the upper side of 72, right? This is clear? Lower tail equal to false, which comes to be, this comes out to be, I think 4217. Yes. So what will I do? I will, from this entire area, I will subtract this area. It will give me this area. Is that clear? Is this clear to all of you? Pradeep says, explain. Anyone else who wants me to explain, or it is clear? Okay, I'll repeat once again. Okay. Okay, are you clear? First of all, are you clear about this? Oh, wait. Are you clear that we need this shaded region? Why you put lower tail equal to false? Okay. See, there are multiple ways you can do it, right? Why did I put lower tail equal to false here? Are you asking this? Yes? Because, see, how will I calculate this area? Tell me. How will I calculate this area? I I I get the area from 50 and above, which is 1 minus this. Is it clear? I got this area as 0.0738, right? When I subtract this from 1, I get this area, entire area. Let's call it area A. Okay, Pradeep, Amatullah, did you get it? Area A, you got it? On the upper tail, right? From this area, to get this shaded area, what should I do? I should subtract this area, which is on the upper side of 72. Yes? Now did you get it? So I mentioned lower tail equal to false so that I get this area, which I have to subtract. Is this clear? Is this clear? Yes? Pradeep, Amatullah, got it? Okay, perfect. Now, so, okay, similarly, there are more questions, but we will not, I have covered a lot of cases in the same question, right? These questions you can try, question 2, question 3 are there, very on the same lines, okay? So you can try these later, right? Now, what we are going to do is we will move on to the next test, that is t-test. Let's go to the Excel. Go to the Excel and tell me when do we do a t-test? Look at the Excel. I'm okay if you even look and reply. When do we do t-test? I want all the conditions. Standard deviation is unknown, population is normal, and n or, not n, or n is less than 30. Okay? Yes? Clear everyone? Right? So these are the main conditions under which you will do a t-test, right? Okay, so let's first understand what is a t-distribution, right? Why do we have this condition that n should be less than 30, right? Very interesting. If you don't know, this is, I think, one of the most used tests, even more than Z, and one of the most interesting of the tests, right? Especially understanding what is a t-test, it's very interesting. Okay, so let's understand the story behind t-test first, right? It was developed by William Gossett from 18. He lived in, I think, Britain, and he worked in Guinness Brewery, right? While working on his job for quality control, right, he invented this, right, t-test. Since he was in a job, he did not want his name to come out, hence he published this under the pen name called Student. So that's why it's called Student's t-test. Okay? Okay. Now coming to very interesting two slides, and this will give you a very good understanding on t-tests, right? First of all is, can you look at these distributions of different colors, right? All these are distributions of t with different n. N means sample size. Different sample size. T distribution, that's why we say T distribution is a series of distribution. It's not a single distribution, it's a series of distribution, as every sample size, being a small sample, has a distribution of its own. So, if you can recall our simulation, right? When n was 5, the distribution was different. When n was 10, distribution was different. When n was 20, distribution was different. But as n approaches 30, right, this distribution approaches normality. So let me explain this. If you can recall from the simulation, and now I think even you can visualize it in your mind, you will get it. If your n is small, let's say 5, right, and you're picking the samples, right, in the sampling distribution of sample means there will be high variability. When n is less, the variability is high. Remember that the variation is high for in the sampling distribution of sample means. If you're not able to recall, let me show it again today. But I'm not going to spend much time today. See, I've already shared it. Already shared it. Okay, what I am saying, if n is equal to 5, 1, 2, 3, can you see the variability? Now let's take n is equal to 25. Oh, 1, right? I'll take 5. Can you see? The variability is so less. That is what I'm saying here, right? So when n is equal to small, notice that n is equal to small means this red one. Can you see? There are thicker tails, heavier tails for red. Can you see the heavier tails for red? Please respond. All you have to do is just listen to me, right? And understand and then respond. Can you see heavier tails for red? Why is it? Because there will be more variability when n is small, right? Hence, there are chances of extreme values. But as n starts to increase 3 to 5 to 20, notice the tails are getting thinner and this the there is more data inclined towards the mean and tails become thinner. Is this clear? Are you getting the logic also? Why the tails become thinner? Because variability reduces as we increase the n size, right? And that this extreme values, that data in these, it gets, you can say, transferred into the data that becomes more near towards the mean. Okay, and when n is equal to 30, you can see this blue line almost approaches the z normality. That is why, can you please share? Of course I will share. Why are you asking this again and again? In fact, I have already shared this. Or if I have not shared, I will share. I've told you, you will not miss. Okay, if I have not shared, I will share it. Please concentrate on the concept right now, right? I've told you, I think right from session 1, I'm telling you, not even a single file I will share in this training, which I will not share with all of you, right? I'll not even a single slide I will discuss that I will not share. Okay, so please concentrate here. Do not worry about the content. Now don't ask the content throughout. I will share each and everything. Okay, please concentrate. Let's concentrate here. are going a bit slow, but that's fine. We will cover up later. Okay, fine. So, did you get it? What I was explaining, that why this shape, and yeah, so that is why this 30 cutoff has come up from where? Can you see this? Now, when n is 30 or more, even for a t test, it becomes a z test anyways. Can you see? Right? T test becomes a z test anyways. That is why this cutoff of 30 has come up. Scientifically, it has come up. It is not randomly someone one fine day they found this cutoff and they just published it. Okay? Very scientifically, it has come up that when n is 30, this t approaches z, and beyond that it just remains z. Okay? Okay, so T distribution, series of distribution, as every sample size, being a small sample size, has a different distribution. It is used in two scenarios: when population standard deviation is unknown and population is normal. We know this also, or when sample size is less than 30. Okay. Next, characteristic of T distribution: symmetric, unimodal, and a family of curve. Of course, you can see this. Flatter from the middle and more area in the tails. And thus, there are more chances of extreme values than the normal distribution. All of you will agree. There are more chances of extreme values in T distribution compared to normal distribution. T distribution approaches standard normal distribution as the n becomes large. This also we have discussed, right? Assumptions of T distribution, they are same as normal distribution. Exactly same, right? No change. This is the formula for T distribution. Again, you don't have to remember this. Now, types of T distribution, right? There are three types of T distribution tests. Understand these well, right? At least these tests are there in Excel as well when you learn the data analysis pack. I don't know how many of you have done it, but I have taught that also when we did Excel. Okay, I think that is if you take any Excel course, then you will learn this also, right? Ashwini, let me share the doc first. That is important. You don't understand. I am telling you again and again, do not worry about the document. I will share it. Again, in between, someone will say something. Okay, from tomorrow I will share it in advance. I think you should be worried more about understanding the concept. Of course, when I've assured you you will get the documents, all the documents, then again I just said this 5 minutes back, and again Just a second. Okay. Now I've shared the documents, right? Even for tomorrow's class, we are going to refer to these only. Okay. Now can we concentrate? Okay. T-tests. There are three types of t-tests that we will do, right? One sample t-test. In one sample t-test, I'm going to compare one mean of one group, means mean of one sample against the population mean. Okay, so this is called one sample t-test. Again, notice you are comparing two sets of data. You are not comparing one set of data, two sets of data. Example, a researcher wants to determine if the average eating time of a standard size burger differs from a set of value that is 10 minutes. Okay, so you are comparing two set of data here, two set data from two distributions, population and sample. Okay, second, independent two sample t-test. The two sample t-test is used to compare the means of two different samples. Means we compare two samples and we try to see whether both of them come from the same population or different population. Like example, compare the average height of male employee with that of female employees, right? We compare the average height of male employees in an organization with the average height of female employees and see whether they both come from the same population. And when I use this term, whether they both come from the same population means whether they have similar, whether they are coming from a population having similar parameters. Okay, so in statistic you say like this, that whether they come from the same population or not. Okay, then third, dependent or paired sample t-test. This is used to compare the related observations. Now this is a very different type of t-test wherein we compare separate means of a group at two different times or under two different conditions. For example, in a uh, yeah, that uh, open air gym example, right? Government government took the sample of males, right, before installing the open air gym. Took the sample of males before installing, right? Then they installed the open air gym to measure the success, whether this was successful or not. They again took the sample. Now, no, it's not cause and effect. No, no, no. See, cause and effect is not the it's not the purpose here. Doing before and after. The purpose is to check the efficacy or the effectiveness of an event. Okay, like government installing open air gym to check whether the installation of open air gym was successful or not. They took a sample before the gym were installed and then the observations, then the weights from that same sample of same people after the gym was installed, let's say 2 years after the gym was installed. Are you getting this point? So the people, the sample remains the same, okay, but it is done before and after. Okay, example is there on the screen, comparing the productivity levels before and after the training program in a company. So the training program was conducted to in an organization, right, to improve the productivity levels. Productivity levels were measured before the program, and then they were measured after the program. Now, what will you do? You are going to do a t-test here. You will do a t-test here to check whether the program was successful or not. And how will you measure whether this program was successful? If the productivity levels have gone up, right, you will say the program was successful. Okay, so we are going to do the t-test for each of these, but now I think we don't have time. We will start with examples of t-test tomorrow. Okay, t-test tomorrow, we'll do t-test ANOVA chi-square, and then we are going to start with the modeling part. First we are going to learn the cross validation. What is cross validation? And tomorrow we are going to start with, I think, regression. We will start. Regression is a very long topic, so it will occupy tomorrow and day after. If we start tomorrow also, it will occupy the whole 3 hours. Okay. Okay then. Right. Thank you so much, everyone, and we'll meet tomorrow same time then.
Thank you so much, Deepak, for the session. And thank you everyone for your participation as well. So everyone, if you have any queries, please post it in the chat box so that we can take it up from there. And I also request you to raise any queries with you post the session by raising a ticket in help and support platform so that our team can take it up and we will respond within 5 to 6 days.
Wait. Hello.
Yeah, Deepak. There are
Just hold
few
on.
queries in community.
No. I'm just. I think I posted in the wrong group then. Wait. I'm just posting. Parametric tests. Just hold on. Okay. Now, just can you check now? Can you check now? Got it? Did you get it now? Got it? Okay, perfect. Over to you. Thank you. Gopika? Okay
Yes,
then.
Deepak.
Yeah,
Yeah.
please.
So
Okay.
thank you so
Thank you.
much, Deepak, and thank you everyone for your time. I have shared the feedback survey link in your chat box. It will be reappearing once we close the session. I request all of you to kindly submit the feedback. If you like the session, please rate us a 5, and for anything less than 5, please share your comments to help us understand what went wrong so that we can improve in that. So thank you everyone for your time. So Amir has posted that the link is not yet working. So Deepak, is the link working right now?
Yeah, I've already shared. Now.
Okay.
They would have got it now.
Okay. Uh, Please wait for another 10 minutes for it to be reflecting on your community link. And if it doesn't appear on your community link and if you're facing any issues with its access or posting a reply, please reach out to us by creating a ticket so that we will look into it. That all the queries are addressed and there aren't any further queries on the chat box. So everyone, take care and we will meet next session if we do not have any further queries. Thank you, Deepak, for the session. Bye everyone.